Good day, everyone. Today we will be continuing our discussion on the different quantum numbers as well as electron configuration. So particularly, we will be discussing now shorthand electron configuration. But before that, let's first review the different quantum numbers that we have learned during our lecture. So we mentioned that we actually have four quantum numbers, and the first three quantum numbers, the shape, the size, and the energy of each orbital again is a function of the three quantum numbers that we have described. Okay, so these different quantum numbers will be describing to us now the location of an electron within an atom or ion. So the first quantum number that we learned is the n, which is the principal quantum number, and this signifies the energy level. And as we have mentioned earlier, for the energy levels, we have 7 energy levels that we can actually find in our periodic table. The second quantum number is signified with the letter L, and this is the orbital, or we also call it as the angular momentum quantum number, and this will now signify the shape of the orbital. And then finally, we have the ML, which is the magnetic quantum number, and this designates now a particular suborbital. Particularly, it is the three-dimensional space which the electrons occupy. The fourth quantum number, as we have mentioned, is not derived from the wave function. And the fourth quantum number is actually S, or the spin quantum number, which now gives us the spin of the electron. I also mentioned to you that for the spin of the electron, it could either be clockwise or counterclockwise. And the number for this will be either 1/2 or negative 1/2. Now, using the spin quantum number, this is what we will be using in determining now or in making now our orbital diagram. However, before we are able to make the electron orbitals or the orbital diagram of different elements, we have to remember three principles. The first principle is off-bow principle, and according to this principle, the off-bow principle, it says that electrons are added one at a time from the lowest energy level orbitals that are available until we reach the electrons of the atom that have been accounted for. Okay, so again, we start from the lowest energy level. For the Pauli exclusion principle, it means that an orbital can hold a maximum of 2 electrons. Now, these electrons should occupy the same orbital and at the same time should have a spin in opposite directions. So one of them will move clockwise, the other one will move counterclockwise. And so we give the value for one will be 1/2, and then the other one will be negative 1/2. The third rule is called Hund's rule. And for Hund's rule, it mentions that electrons actually occupy equal energy orbitals so that our maximum number of unpaired electron will give us now the result. So let's take a look at these different principles one by one. Let's start with the Pauli exclusion principle. As we have mentioned, for the Pauli exclusion principle, these orbitals can actually contain a maximum of 2 electrons. And as I mentioned earlier, they will have opposite spin. Okay, one of them will go clockwise, the other one will go counterclockwise. So we give the number or we give the value 1/2 for the first, and then the second one will be negative 1/2. The second principle, according to Aufbau principle, he said that we need to add electrons one at a time. We will start with the lowest energy level until all the electrons of the atom have been accounted for. So again, we will start with 1s because this is our lowest energy level. Then we go to 2, that will be the 2s, and then go to 2p. Then we go to 3, 3s, 3p, and then we go to 4s before going back to 3D, okay? And then we go to 4p, 4D, After that, we go to 5s, sorry, we go to 5s, and then we go to 4d, and so forth and so on. So again, how do we do that? We just follow the diagonal rule that we have discussed in getting the electron configuration. So again, electrons should fill the lowest energy orbitals first. The last rule that we need to remember is the Hund's rule. Okay, so for Hund, or the Hund's rule, it says that within a sublevel, you have to place one electron per orbital before you pair them. So in order for us to remember this, just remember the empty bus seat. So what does the empty bus seat mean? So in the empty bus seat, if you notice, for example, you go inside the bus, what you do is you actually ride, or you go to the seat that does not have a partner. Okay, especially if the buses don't give you tickets, you can just sit anywhere. Of course, what you look for is the chair that do not have or that is not yet occupied. So that's why we call it empty bus seat rule. And then afterwards, when every seat is already occupied, that's the time that you go to the one that will have another person beside you. Okay, so that's why it's called the empty bus seat rule. Okay, so take note of these three principles, and by using these three principles, we can now make our orbital diagram. For example, we have oxygen. Okay, let's try oxygen. How do we write the orbital diagram for oxygen? So of course, we need first to get the electron configuration of oxygen before we are able to get, or before we are able to make its orbital diagram. So for example, for oxygen, it has 8 electrons. So we have one s, and then for s, we have 2 electrons with opposite direction. The next one is 2s. So again, for the 2s, it has only one orbital, and so 2 electrons inside this orbital. And then for 2p, we have 3 boxes. Why 3 boxes? Because remember that for p, it has 3. Okay, and so we put now the different electrons, 1 electron per orbital first before we pair them. So now the electron configuration for oxygen is 1s2, 2s2, and 2p4. So if you count the electrons for p, that will be 1, 2, 3, and 4. Okay, let's try these different elements. They are also the exercise that we have done in the electron configuration. So let's first try with nitrogen. Okay, how do we write the orbital diagram for nitrogen? So again, for nitrogen, okay, we actually have, okay, so the electron configuration for nitrogen will be 1s2, 2s2, and then 2p3. So how many electrons does nitrogen have? We have 7 electrons. Okay, so now that we have written its electron configuration, the next thing that we do is we draw boxes. So we have one for S, one box for S also, and then for P, we have 3 boxes because it has 3 orbitals. Okay, next is we put the electrons in the lowest energy level first. So we will start with S. So one in counterclockwise, the other clockwise, and then the other counterclockwise. And then for 2, it has 2 electrons. So one spins in clockwise, and then the other spins counterclockwise, and then 2p3. So we follow the empty bus rule. So we fill up each of the seats first, or each of the boxes first, before we pair them. So that's 3 electrons. We have 1, 2, and 3. So this is the orbital diagram for nitrogen. Okay, let's try the second one. We have neon. For neon, we have 10 electrons. Okay, and so the electron configuration for neon will be 1s2, 2s2, 2p6. Again, we put boxes that will signify the different orbitals. So 1 for s, 1 for s again, and then for p, it will have 3. So 1, 2, and 3. And then next, we put now their different electrons. So for s, 1s, we start with the lowest energy level. So for 1s, we get 1 and 2 electrons. Both of them have opposite direction. For 2s, 2 electrons again. So that's 1 and 2 electrons. And then for 2p, we only have, or we have 6 electrons. So again, empty bus seat rule or the Hans rule, we start to fill up all of the boxes first before we pair them. So 4, 5, and 6. So that's how we write the electron configuration and orbital diagram for nitrogen and neon. Okay, let's try another one. How about for potassium? So for potassium, we have 19 electrons. Okay, and so the electron configuration for potassium would be 1s2, 2s2, 2p6, 3s2, and then we have, okay, let's put some space there. Okay, that will be 3s2, and then we have 3p6 and 4s1. Okay, so that's the electron configuration for potassium. Next, we draw the different boxes for the different orbitals. So for S, we have 1. For P, we have a 3. For S, again, we have 1. For P, we have 3. And then 1 again for S. Okay. And then next, we write now their different spins or different electrons inside the orbitals. So for S, we have 2 electrons. For 2s2, again, 2 electrons. For 2p, we have 6. So that's 1, 2, 3, 4, 5, 6. For 3s2, we have 1 and 2. And then for 3p, again, we have 6 electrons. So that's 1, 2, 3, 4, 5, and 6. And then finally, for 4s, we only have 1 electron. So we just write 1. Okay, so again, that is how we write the electron configuration for potassium. Lastly, let's try zinc. Okay, so what will be the orbital diagram for zinc? Okay, so for zinc, the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. Okay, so that will be the electron configuration for zinc because it actually has 30 electrons. Okay, so again, we draw the boxes. So we have one for S, another for S. For P, we have 3. For S, again, it has 1. For P, again, it has 3. For S, it has 1. And then when we go to D, it will now have 5. Okay, so 1, 2, 3, 4, and 5. Okay. Okay, next. So we now draw their different spins. Let's start with the S first. Okay, for S, we have 2 electrons. For 2s2, 2 electrons. For 2p, that's 6 electrons. 1, 2, 3, 4, 5, and 6. Then for 3s, it has 2 electrons. For 3p, it has, again, 6 electrons. For 4s, it has 2 electrons. And finally, for 3d, it has 10 electrons. So this means that we will be filling up the electrons of, okay, there. So we will be filling up the electrons for all of the orbitals that we have, okay? In our previous lecture, we have learned about the different quantum numbers. And the second quantum number that we have learned is actually the angular momentum quantum number, which is signified with the letter L. We said that the angular momentum quantum number gives us now the shape of our different orbitals. We also have what we call the magnetic quantum number, which give us now the 3D or the three-dimensional space of the orbitals. And the magnetic quantum number is signified with the letters ML. So let's now talk about atomic orbitals. Atomic orbitals are defined as a three-dimensional space where the electrons can most likely be found. And if you remember the principle of Heisenberg uncertainty principle, we said that we cannot actually pinpoint the exact location of these different electrons. However, we can say that there is a three-dimensional space, and most likely these electrons are located in that three-dimensional space. For atoms, we call this as atomic orbitals, whereas for molecules, we call them as molecular orbitals. Now, in a wave or a quantum mechanical model, the electron now is described as occupying a three-dimensional space. Again, where can we find this three-dimensional space? It is actually surrounding the nucleus. We may not be able to pinpoint the exact location of the electrons, but we know that they are somewhere in the three-dimensional space. Now, the nucleus is also described as being surrounded by an electron cloud. Again, the electron cloud is most likely where the electrons are found. Now, let's talk about the different orbitals and let's see how would they look like. The first orbital is called the s orbital. And in the s orbital, it is actually spherical in shape. Now, whenever you increase the value of n, which is the increasing energy level, the radius of this sphere is actually increasing. So if we look at this 1s, it has a smaller radius compared to 2s, which has a higher energy level. And when we compare it again to the 3s, which again has a higher energy level, the radius is increasing. Take note that as n increases, the number of nodes also increases. What do we mean when we say node? This is a region in space where the probability of finding an electron is 0. However, if you notice for the s orbital, it actually does not have a node. So for an s orbital, the number of node is n-1, which is 1 minus 1, so 0, which means that for the s orbital, we actually do not have a node. The second type of orbital is what we call as the p orbital. And for the p orbital, it is actually like a dumbbell, so it's dumbbell in shape. Why? Because it has two lobes. These are the lobes. And then in between them, we can find now a node. Again, when we say node, this is the place where you can, the probability of finding an electron is 0. Now, there are three p orbitals. We have the px, the py, and pz. If you remember, we said that for the p orbitals, there are 3. So, again, in the three-dimensional, we can find them in the px. This is the px. We have also the py. So this is the py. And then we have the pz. Okay, so this is the pz. Now the orbitals are dumbbell in shape. And of course, as n will increase, the p orbitals also will get larger. And take note that all of these orbitals, if you notice, all of them will include now a node in between them. The next orbital is the d orbital. So for the d orbital, they are now located into 5 different three-dimensional spaces. And since the d orbital, the value of L is now 2, which means that it will have two nodal planes. So again, for the node, we get n minus 1. So the value of L is actually 3, so minus 1, then we get 2. So this means that it has two nodal planes. If you notice, again, it's still the same with the p orbital, but we get now two dumbbell shapes. And so the first one, the first plane is where we can find the node, and then the second plane is where we can find the other node. Okay, so it has now two nodal planes. Now, if you notice, 4 of these 5 different orbitals have 4 lobes. So we have 1, 2, 3, 4. However, for the fifth orbital, or for the fifth d orbital, it looks like a p orbital, and then we put a donut around the center. Okay, so this is how the fifth d orbital would look like. The last one is the f orbital. And again, for the f orbital, the value of L will be equal to 3. This means that it now has 3 nodal planes. If you remember, again, it's n minus 1. So that would be 4 minus 1. So we have the 3 as its L, or 3 nodal planes. And for the letter F, or the f orbital, it actually have 7 orbitals. So that's the sublevel. So it means that it's located in 7 three-dimensional spaces. Okay, so again, if we look at this, they look like they have different lobes. So how many lobes? It has actually 6 lobes for the 6 of the different suborbitals, and they are located with 3 nodal planes. However, for the last suborbital or sublevel of f orbital, it will contain now a dumbbell shape, and then it has 2 donuts in between. So this is how our f orbital would look like. Now take note that the closer to the nucleus, the lower the energy. And if you notice, in the electron configuration that we have been doing in our practice exercise, the d and f orbitals are always in the lower energy levels. So why is this happening for the d and f orbitals? Okay, let's take a look at this one. So in the electron configuration, what we do is we follow the diagonal rule. So for example, we have 1s, then the next one we go to 2s, the next one we go to 2p, and then the next one we go to 3s, the next one we go to 3p. However, instead of going directly to 3d, we skip 3d, but instead we go to 4s. And then afterwards, we go to 3d, and then 4p, 4d, and so on, and so forth. So why do we follow this in writing the electron configuration? Okay, it's because the d and f orbitals actually require large amounts of energy. And it's actually better for us to skip a sublevel that would require now a large amount of energy for a one that is in a higher level but lower energy. So again, if we go back to our diagram a while ago, it's better for us to skip 3D because it has a higher energy than 4S. For 4S, it actually has a higher level, but it has a lower energy than the 3D. Okay? And so it would be better for us to skip that and then proceed to the higher level with lower energy. This is the reason why we always go first to the S before the D, and of course we go to the P before the F. So take note, this is the reason why we follow the diagonal rule. Be sure that you have to follow the arrows or the order of the arrows in your diagonal rule so that you won't be skipping or you won't be going to the higher energy levels or the sub-level with very high amount of energy, but rather you skip that and then you go first for the higher level with lower energy. Now, let's talk about shorthand configuration. Last time we actually discussed how to get the electron configuration of different elements, and particularly we did the longhand method. Now we will be talking about the shorthand method in getting the electron configuration. For example, we have here the electron configuration, which is Ne3s1. This is actually the electron configuration, particularly the shorthand configuration of sodium. And for sodium, the longhand configuration is actually 1s2, 2s2, 2p6, 3s1. Again, its shorthand would be Ne3s1. So what do these symbols mean? The Ne here, okay, will actually be the neon's electron configuration. So the electron configuration of neon is 1s2, 2s2, and 2p6. And then we have here 3, that means that it is in the third energy level. And then we have here S, which is the orbital shape, and then 1 here is now 1 electron in the S orbital. And so, when we do shorthand configuration, what do we need? We actually need the core electrons. This is going up 1 row and over to the noble gases. Take note, all of the core electrons that we will be getting will be from the noble gases. And we also need the valence electrons. So this is now the next row after the noble gases. We fill in the number of electrons in each of the sub-level. Now, please memorize or please take note of these different sub-levels in your periodic table. Here in this area would be the S, and as we have mentioned before, the S orbital will have a maximum of 2 electrons. And then here in this area, the lower part of our periodic table is the F orbitals or sub-level. And then take note that when we go to the F, we will be using n-2, meaning if, for example, you are in the 7th energy level, so we will be getting 7 minus 2, then it becomes 5. Okay, in this area, this is the D level. Okay, and again we use n-1. So for example, if we are in the 6th energy level, -1, so it becomes 5D instead of 6D. And then in this part, it's actually the P sublevel. And then again, for the P sublevel, how many electrons does it have? It actually have 6 electrons. Now, if you notice here, we have the yellow. Okay, this is actually included here. So hydrogen, then helium. So this one is also included here. Okay, let's take a look at this example. So we have here germanium, and if you notice, germanium is located here in your periodic table, and also it has an atomic number of 32, which means that it will have 32 electrons. So how do we write now the electron configuration of germanium using the shorthand method? So the first step that you need to do is you have to go up 1 level to the nearest noble gas. So again, go up 1 level, okay, and then we go to the nearest noble gas. Okay, so germanium is found in the 4th energy level. Then we go up, and then we go to the nearest noble gas, and then we write that noble gas. This one is actually argon. Next, after you write the noble gas, we will now fill up the electrons here as in the 4th energy level until we reach germanium. Okay, so again, so this is the first energy level or sub-level, so that will be 4s, and then how many electrons? It has 2 electrons, so 1 and 2. Next is, this will be the d orbital. Okay, so for d orbital, we said that it should be minus 1. So for minus 1, it becomes, instead of 4d, it becomes 3d. So that will be 3d, and then you count the electrons. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it becomes 3d 10. Okay? And then finally, we go back to P. So this one is P. So we have, again, it's in the fourth energy level. So we put 4p. However, we only have 2 electrons left. So that's 1 and 2. So we write 4p2. So this is how we write the shorthand configuration for germanium. Another example is for sulfur. So again, for sulfur, it has 16 electrons. So the longhand configuration for that will be 1s2, 2s2, 2p6, and 3s2. So it's actually in the third energy level, okay? 3p4. So these ones are what we called as the valence electrons because they are in the outside orbitals. Okay, now this one that we have here are what we call as the core electrons. So the core electrons will now be the electron configuration of the noble gas. And so if we did the shorthand configuration for sulfur, that will be neon, that's 1s2, 2s2, 2p6, that's the electron configuration for neon. And then afterwards, we write its valence electron, which is 3s2 and 3p4. Now let's try to get the shorthand configuration of different elements. And we will be using again our periodic table. So we need to get our periodic table in order for us to solve for their different electron configuration. So let's try first to get the electron configuration of, for example, calcium. Okay. Okay, let's write calcium. And if you notice, in the periodic table, the atomic number of calcium is 20. So this is calcium. Okay. So please take note. We have here calcium. So that's calcium. Okay. So we write 20 for its number of electrons, or that will be its atomic number. Okay, so again, how do we go, or how do we actually write the electron configuration of calcium? So as we have mentioned earlier, first is you go up one level. So since calcium is in 4, we have to go up one level, and that will be, for calcium, that will be 3. And then we go to the noble gas above it. So the noble gas above it will be this one. That will be argon. Okay, so again, argon will be our noble gas. So we just write, okay, we just write argon, and the argon should be inside a bracket. Okay, next, after that, we count how many electrons are left. So again, we will be going back to our energy level. So this is our energy level. Okay, take note, this is our energy level where calcium is found. So we write 4. Okay. After that, we count how many electrons for calcium until we reach calcium. So that will be 1 and 2. Okay, so then we write for S. Remember that I said earlier that for this part, this is the S. And then for this part, this will be the D block. This part will be for the P block. And then this part will be the F block. Okay, so please do not forget that. And so going back to calcium, we have 4s, and then it has 2 electrons. So now we get the shorthand configuration of calcium, which is argon 4s2. Okay, let's try another example. Okay, what if we get the electron configuration, for example, of vanadium? Okay, where can we find vanadium? It's again in the fourth energy level. And the atomic number is 23. So we have, for vanadium, we have 23 electrons. Okay, so again, we go to the um uh, one level higher. Okay, and then we go to the nearest noble gas. So that will be for vanadium. We go one higher up. So that will be again same. It's argon. So we will be writing for its electron configuration. We write argon, okay, inside the bracket. Okay. Next, we will be counting how many electrons per level. Okay. So again, vanadium is in the fourth energy level, so we start with S. So this is S, that's 1 and 2. So we write 4. This is the energy level where vanadium is found. So we write 4. And then for S, it has 2 electrons. Now, I said earlier that for the letter D, we put D is equal to n minus 1. So if for example, if the energy level is 4, okay, for if the energy level for D is 4, okay, that will be 4, we will minus 1. So what do we get? We actually get 3. Okay, so instead of writing 4, what we write now is 3. Okay, so remember again, what do we put there? We put 3, and then we are already in the D block. Okay, so we put 3D. Next, we count how many electrons does it have. So that's 1, 2, and 3. So we write now electron 3D. 3D3. Okay, so please do not forget that. That is how we put now the electron configuration for the shorthand of vanadium. Okay, so let's try another one. And this time we'll put, let's say we have silver. Okay, so that will be Ag, silver. And where can we find silver? If you look at your periodic table, it is here. The electron configuration for silver is 40. Oh, sorry, the number of electrons for silver is 47 electrons, following its atomic number. Okay, so again, what is the first thing that we do? We go up one energy level or one row higher. So that will be, okay, that will be we go to the fourth because again it is in the fifth energy level, so we go to the fourth energy level and we go to the nearest noble gas, so we go to krypton. Okay, so again we write inside the bracket, we write Kr, that's the symbol for krypton. Next, we go back to its original energy level. So again, we start with the S block. This is the S block again, okay? So we start with the S block. So we have 1 and 2. We write the energy level first, which is 5. So 5s2. Okay, next we go to the D block. So this is the D block. And again, as we have mentioned, for the D block, that is n minus 1. And so since n is 5 minus 1, then instead of writing 5, we write 4. Okay, so that will be 4D. And then we count how many electrons does it have. So that will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so for silver, the electron configuration will be krypton 5s2 4d9. Okay? Okay, let's go to the last example. and we'll write now, let's try iodine. Okay, so what will be the electron configuration for iodine using the shorthand? So first, again, we find the iodine in the periodic table, and it's actually found here in number 53. So the number of electrons for iodine will be 53 electrons. Okay, again, as I have mentioned earlier, the first thing that we do is we go one row higher. So, and then we go to the nearest neon gas. So the nearest neon gas for iodine will be, we go up one and then we go to krypton. Okay, so again, it's krypton. So we write Kr inside the bracket. Okay, next we go back to its energy level. Again, what is its energy level? It's number 5 still. And then we write now the different electrons in each of the orbitals. So for S, it has 5s. And then how many electrons? It's 1 and 2. So that will be 5s2. Next is we go to D. So again, for D, we have n minus 1. So it will be 5 minus 1. So we will have, or we will write 4D. Then we count the electrons. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it has 10 electrons for D. Next, for this block, it's actually the P block, and we go back to its original energy level. So we write 5 and P. And then we count how many electrons is in the P block. So that's 1, 2, 3, 4, and 5. So we write 5P5. Okay, so this is how, again, we write the different shorthand electron configuration of our different elements using the shorthand configuration. So you just look at your electron configuration or your periodic table, you will be able to write now the shorthand electron configuration. Okay. Okay, so now let's try again these different elements. So this will be your practice. So we already did the first 4. So that's for calcium. We have for vanadium. We have for fluorine, for silver, and for iodine. So your practice will be the next 3 different elements. So you have to find out which element is this, which element is this, and then you have to write the correct shorthand configuration, and then what is the electron configuration for this element. Okay, so thank you, and I'll see you again for the next lecture.